Welcome to the solution part of problem 4.9. Let's just get straight to work. In part A, we're asked to find the kth moment of the zero modified version of m. So what we're asked to do is to find the mean of n to the k. So let's just get started. By inserting the definition of n, what we see is that this expected value is just equal to I to the kth multiplied by m to the kth, right? Now, what we know is that since I and m are independent, so I will just write that up here. So I and m are independent. So because of that, we also know that a function of I will be independent from a function of m. So that means that I to the k and m to the k are independent. And since the mean of two independent variables is equal to the mean of the product of two independent variables is equal to the product of their means, we can just split up this expected value into the expected value of I to the k multiplied by the expected value of m to the k. So in this exercise, we are asked to express this expected value with p and the expected value of m to the k. So we're done with this part, we just need to finish off this part. So what is the expected value of I to the k? Now, if you remember the definition of a Bernoulli distributed random variable from the book, then also in the book you actually get the values of that variable's kth moments. However, we can just calculate it very quickly here. So the mean of I to the k is equal to, well, the first value that I to the k can take is 0 to the k, multiplied by the probability of it taking that value, which is just a probability that I is equal to 0, then plus the second value that it can take, which is 1 to the k, multiplied by the probability that that will happen, which is just probability that I is equal to 1. So it cannot take any other values, so we don't have to add any more terms to the sum. This is just 0, and what we get is that the kth moment of a Bernoulli distributed random variable is just 1 multiplied by its success probability p. Hence, this is just equal to p multiplied by the expected value of m to the k. So what you have to be careful of here is that you don't write p to the k. That has happened for a couple of you guys, and I'm guessing it's because of some kind of weird accident that happens up around here. Anyways, this is the expected value of the kth power of n. So the kth moment of n is given by the kth moment of m multiplied by the probability that m is greater than 0. Or multiplied by the probability that I is equal to 1. Sorry, not that m is greater than 0. Okay, so the second part asks us to find the variance of n. So we are asked to find the kth moment of n and also the variance of n. So as we noted earlier on, the variance of a stochastic variable is given as its second moment, so the expected value of n squared, minus the square of its first moment. So the second moment of n we can find from earlier in the exercise. It's p multiplied by the second moment of m. And the mean of n is p multiplied by the mean of m, which we have to take squared. So that gives us p squared multiplied by the mean of m squared. And some of you might say, well, seems like we're done now. There's not that much more we can do. However, with this kind of exercise, often the kind of solution we're looking for when we're looking to express the variance of n is to express the variance of n in terms of the variance of I and the variance of m. So if we think of it in that way, then we are far from done. So what can we do? Well, we noted before that the variance of something is given as the second moment minus the first moment squared. So that actually means that if I were to try and in some way incorporate the variance of m inside this expression, well, I can sort of do that, right? By replacing its second moment here, since I know that the second moment of x is equal to the variance of x minus its squared of the first moment for any stochastic variable x. So in particular for m, what we have is that this thing here is equal to p multiplied by the variance of m minus the second, minus the square of the first moment of m, and then, sorry, is it minus? It's supposed to be a plus here, isn't it? Yeah. Move this over here, it's a plus. So plus the second, the square of the first moment of m, and then minus p squared multiplied by the square of the first moment of m. So I have two terms here that can be collected into one term, and what I'm left with is p multiplied by the variance of m plus the mean of m squared multiplied by p minus p squared. So this is actually recognized to be the variance of I. And the reason for that is because the variance of a Bernoulli distributed random variable is equal to p multiplied 1 minus p, which is exactly what we have written here. So you can either recognize the variance of I, or if you don't recognize it, at least we are more done now than earlier, since now we just have the variance of n in terms of the variance of m, and then the mean of m, and then just multiplied with some numbers that we know are all positive. So this is the variance of n, guys. And what we can sort of use this for later is to show that n is overdispersed if m is Poisson distributed. So this will be this video. In the next video, we will try to look at the point probabilities of n.